system, the refrigerant can change its phase. So it may be from solid to liquid or from liquid to solid. And the four processes consists of isentropic compression, and the heat action is isobaric. Okay, isobaric, and also the heat abstraction is also isobaric, whereas the expansion is throttling. Okay, next. So we have seen the four components required already. So compressor, condenser, expansion valve, and then an evaporator. You can see the TS diagram for the saturated cycle. So that is the saturated cycle. So 1 to 2 is compression, isentropic compression, and 2 to 3 is heat rejection in the condenser, and 3 to 4 is isenthalpic expansion in the expansion valve or the capillary tube, and 4-1 is the actual refrigeration effect produced in the evaporator. So why it is called as saturated cycle means, so at the suction of the compressor, the refrigerant is dry and saturated vapor, and similarly at the end of the condensation, so the refrigerant is saturated liquid state. So that's why it is called as saturated or simple saturation cycle. And this is the most widely used cycle for the refrigerators or for the air conditioners. And the main advantage is that it can be from very low capacity, 0.5 tons to even more than 250 tons of refrigeration can be produced by vapor compression refrigeration system. And the refrigerant can be any refrigerant. Then the properties required we will see later. Next. And we have seen the variations from reversed Carnot cycle also. Reversed Carnot cycle is the ideal cycle, so which is not possible practically, but the coefficient of performance of the reversed Carnot refrigerator will be maximum. So whereas vapor compression refrigerator coefficient of performance is also maximum, but that will be always lower than reversed Carnot cycle, but it can be maximum up to 0.6 times the COP of reversed Carnot cycle. And the main three deviations what we have seen is, so you can see the cycle from the slide here. So here the reversed Carnot cycle is 1, 2, double dash, 3, 4 dash. So that is a rectangle. And for the vapor compression refrigeration cycle, it is 1, 2, 2 dash, 3 to 4. So the main three deviations from the reversed Carnot cycle for vapor compression cycle is, so there are only three deviations. What are the three deviations? Are that the refrigeration effect is reduced due to the throttling expansion. Okay, so that area is represented by area under 4 dash. So that is 4 dash CD represents the loss in the refrigeration effect due to the throttling expansion. And the other deviation you can see is the work is also increased in this vapor compression refrigeration cycle by the area 43F. Okay, so that is at the left of the TS diagram, 43F. So that area is same as that of 4 dash CD. Okay, so that is the extra work required for the compressor. So whereas in the reversed Carnot cycle we can able to get some expanded work, with that the work input to the compressor can be reduced. So that is not the case in the vapor compression refrigeration cycle. And the other deviation is that you can see from the TS diagram 2 dash to 2 double dash. So that is called as the superheat horn. Okay, so that is the extra work required for running the compressor. Okay, so compared with the reversed Carnot cycle. So these are the three main deviations from the reversed Carnot cycle, with which the COP of the vapor compression cycle is always less than that of the reversed Carnot cycle. Next. And we have seen the wet compression and also dry compression. Okay, So in the compression process or in the compressor here, when the refrigerant at the suction of the compressor is in the wet state, okay, having some dryness fraction, then that compression is called as always wet compression. If at the beginning of the suction of the compressor, if refrigerant is dry and saturated, then it is called as dry compression. Okay. So always we have to cover the suction of the compressor, not at the discharge of the compressor. So with wet compression, always some disadvantages are there. So always it is better to see that at the suction of the compressor, the refrigerant is always dry and saturated state. So what are the disadvantages of wet compression is, so the liquid refrigerant may be trapped in the head of the cylinder and may damage the walls or the cylinder head. So whenever some moisture is present here, always there will be wear and tear on the walls or head of the compressor cylinder. Then the droplets of the liquid refrigerant may wash out the lubricating oil from the walls of the cylinder, thus again accelerating the wear. Okay. So in the reciprocating compressor, the type of the compressor is used in vapor compression refrigeration. The type of the compressor used is generally hermetically sealed compressor. Okay. So in that always, if at the suction of the compressor some wet vapor or this wet compression is taking place, always there is chance of removal of the lubricating oil present, which will again accelerate the wear and tear on the compressor also. Okay. It also reduces the refrigeration effect. Okay. So these are the main disadvantages of wet compression, and always dry compression is preferred. Okay. Or even sometimes even superheating condition may be at the suction of the compressor. So that depends also on the type of the refrigerant used. So it is always not the same thing for all the refrigerant. So for some refrigerants, even wet compression is also preferred rather than dry compression also. So that depends upon the type of the refrigerant. But there will be some tear and wear will be always on the cylinder head with wet compression, and also removal of the lubricating oil. So whenever lubricating oil is not there, then the work required for the compressor will also be more. Okay. So whenever the work required will be more, so that will reduce the coefficient of performance of the vapor compression cycle. And for the analysis of the vapor compression refrigeration system, so the main parameters required for doing any problem or for designing any vapor compression refrigeration system, the load on the evaporator in tons of refrigeration, whatever the load that is required, so that is to be known, and the temperature required in the evaporator, is it 0 degrees centigrade or minus 40 degrees centigrade, or sometimes even minus 150 degrees centigrade may also be required in the evaporator. So that temperature is also important. Then the atmospheric temperature. So whatever the temperature to which the heat rejection takes place. So that is also very important. So with all this, we can able to find what is the suction pressure and what is the discharge pressure required for the compressor. And also the design of the compressor. So is it for the compressor, is it the different types of compressors, reciprocating compressor or axial flow compressor or centrifugal compressor. So which type is generally used for wet compression or dry compression? When volume flow rate required is less or pressure ratio required is more. Okay. Whenever the pressure ratio required is more, then always reciprocating compressors are preferred. Okay. When pressure ratio required is less, then one type is preferred. Okay. And depending upon the compressor also, the suction of the, so at the suction of the compressor, the refrigerant may also change its state. Then condenser. Condenser is nothing but a heat exchanger. So what is the inlet temperature of water used for condensation? What is the exit temperature? So is it parallel flow heat exchanger or otherwise counter flow heat exchanger? So that is to be known here. And evaporator. So evaporator is also a heat exchanger. So what is the length of the evaporator tubes required? What is the diameter of the evaporator tube required? So that all depends upon the how much heat is to be removed from the evaporator. Next. And we have already seen superheating of the refrigerant. At the suction of the compressor, if the refrigerant is in superheated condition, okay, then the work required for the compressor will always be more. Okay, so that may increase the refrigeration effect, but it will also increase the work input. Okay, so superheating is preferred or not preferred depending upon the increase in the refrigeration effect or depending upon the increase in the work input. So already we have discussed this point also. Let us see what are the various sources of superheating of the refrigerant. So there is automatic control of the expansion valve on the flow of the refrigerant. So whenever there is automatic control, so it may lead to superheating of the refrigerant at the suction of the compressor and picking up of superheat by the vapor after leaving the evaporator, but through passing the piping located within the cool space. So here superheating is also possible. So whenever some heat is taken away from the piping, okay, at the suction of the compressor, and also pickup of superheat in the connecting piping, so increases the compressor. So always superheating increases the compressor work. So first two is automatic control of the expansion valve. So with that always it will reduce the evaporator temperature. So whenever evaporator temperature increases, what will happen to COP? So already we have seen when the suction temperature decreases, when the exit temperature increases, and similarly the suction pressure decreases and discharge pressure decreases. Okay. So if the pressure varies like that, here whenever there is decrease in the suction pressure and increase in the discharge pressure, work input will always be more. So last class we have seen with the number of diagrams also. Okay. So the first point is automatic control of the expansion valve, the flow of the refrigerant. So with this what will happen is, so whenever there is superheating at the suction of the compressor, so the refrigeration effect will also increase. So the first point is a positive point which increases the refrigeration effect. So similarly the second point also increases the refrigeration effect. Whereas the third point, it will increase the work input. So whenever the work input increases, always the coefficient of performance decreases. So you can see from the TS diagram. So at the suction of the compressor, when it is dry and saturated, the compression process is shown by 1, 2. Okay. So with this, the refrigeration effect is represented by the area under 4, 1. Okay. With superheating at the suction of the compressor, so it changes to 1 dash, 2 dash. So with this, the refrigeration effect is increased by the area under the curve 1, 1 dash. Okay. So the work input is also increased by the area between 1, 1 dash and 2, 2 dash. Okay. So whenever the increase in refrigeration effect is more compared with the increase in the work input, always COP increases. Okay. But superheating is always not preferred also. Okay. Then heat exchangers already we have seen. The two heat exchangers used in the vapor compression cycle is condenser and the evaporator. Okay. So when larger evaporator is required, when larger condenser is required, when the size of the evaporator and the size of the condenser. So these are also very important for the design of the vapor compression refrigeration system. So higher suction pressure to give denser gas entering the compressor and a greater mass of gas for a given swept volume. So higher refrigeration duty here. So larger evaporator is required whenever the temperature required in the evaporator is very less. Okay. So for example, some 40 degrees centigrade is the required temperature in the evaporator. Okay. Then the size of the evaporator required will always be more compared with the evaporator temperature at 0 degrees centigrade. Then similarly higher suction pressure. So when the suction pressure increases, so it will lower the compression rates. So whenever the suction pressure increases, so the compressor work will be reduced, which will also reduce the evaporator size. Okay. And similarly the condenser. So condenser is also very important in the vapor compression cycle. So the temperature at which the condensation takes place, okay, that is also important. So that depends upon the pressure required in the condenser. So when the condensation temperature is some 50 degrees centigrade required, then the size of the condenser required will be always more. So lower condensing temperatures is always advisable, and also higher evaporator temperature is always advisable to maintain the COP high. So for the problems here, we have seen that 1 to 2 is isentropic compression. So with this, the work required for the compressor is H2 minus H1. Okay, so that is a specific work required. So that is H2 minus H1, so many kilojoules per kg of the refrigerant. Then 2 to 3 is nothing but here heat rejection in the condenser. So here the heat is rejected in so two steps. So 2 to 2 dash is nothing but D superheating, and 2 dash to 3. So that is again latent heat removal from the vapor refrigerant. Okay. So for here for doing the problems here, so the temperature T2 is very important. So that can be done by number of ways. We will see how to find out T2 also. Then what is the heat rejected in the condenser is H2 minus H3. Okay, if you know the enthalpy at 2 and also the enthalpy at 3, then you can directly find out what is the heat rejected in the condenser. So here H2, that depends upon the state of the refrigerant at 2. Is it in superheated condition or saturated condition? So that you have to find out first. Then 3 is the point here, that is on the saturated liquid line. So directly from the tables you can find out H3 because that is in the liquid state. Then that is the heat rejected H2 minus H3, and also 3,4 is the isenthalpic expansion process. So isenthalpic process. So whereas this is in the capillary tube or the expansion valve. So at 4 you have to find out what is the dryness fraction to find out the enthalpy of the refrigerant at 4. Okay, how to find out the enthalpy at 4 is that depends upon the dryness fraction. So first thing is, first you have to find out the dryness fraction at 4. Okay, so that you can find out from knowing H3 minus HF4 by H1 minus HF4. So after finding the dryness fraction at 4, you can find out the enthalpy at 4. So that is H4 is equal to HF plus X into HFG at the pressure, that is the evaporator pressure. So here the evaporator pressure is represented at the bottom, whereas the condenser pressure is represented at the top. So that is the constant pressure processes, heat rejection and heat abstraction are the refrigerating effect produced. So with that we can find out the refrigerating effect. So that is from the process 4-1, H1 minus H4. And so this is the pH diagram. So directly, so you can see the pH chart just like Mollier diagram. So you have used Mollier diagram to find out the properties of the steam at various conditions. So in the same way here also you can find out the properties of the refrigerant for any refrigerant. So it may be carbon dioxide or ammonia or any freon. So the diagrams are available. So directly you can find out the enthalpies. So here 2 is nothing but the discharge condition for the compressor. So you can find out T2 or H2. Okay, you can find out H2 directly from the pH chart, or otherwise by equating the entropy at 1. Okay, entropy at 1 can be directly seen from the refrigerant tables. Okay, so after finding the superheating temperature at 2, so you can find out the enthalpy at 2. Okay, so S1 should be equated to find out the superheating temperature at 2. Okay, how to find out that S1 is equal to, okay, so S2 minus, so S1 is equal to, you can find out the entropy at 2. Entropy at 2 is nothing but, so from knowing the specific heat and ln T2 by T2 dash, okay, equating with S1, you can find out the superheating temperature. After finding the superheating temperature, you have to find out the enthalpy at 2. Okay, enthalpy at 2 can be known by adding H2 dash with the specific heat of vapor, specific heat of the vapor refrigerant into T2 minus T2 dash. Okay, so specific heat at T2 dash. So you know the specific heat of the vapor refrigerant. So that will be given in the problem. Okay, so that should be multiplied with T2 minus T2 dash. So that is nothing but the superheating. Okay, that is the heat available in the vapor which is in the superheated condition. So that is to be removed. Okay, so that is equal to Cp of vapor into T2 minus T2 dash plus, so that should be added with the enthalpy at 2 dash. So that is nothing but enthalpy at 2 dash is nothing but the saturated vapor condition. Okay, at that pressure, condenser pressure, you have to see what is the enthalpy of the saturated vapor. If you add that, you will get H2. Okay, so H1 you can directly get from the tables. So which is nothing but the saturated vapor condition at the pressure T0, that is the evaporator pressure. So similarly, you can get T2 after knowing, you can get H2 after knowing T2, the superheating temperature. And similarly, you can find out H3 also. So directly from the tables, so that is the liquid refrigerant at the pressure of condenser. So that also you directly know. Then for H4, you have to find out the dryness fraction. After finding the dryness fraction, you can find out H4. So there are the methods by which you can find out T2. Or otherwise, the other method is by using interpolation also. So you know what is H2 minus H1. So directly H2 minus H1. So that should be equated to the difference between S2 dash, S2 minus S1. Okay. Next. And the refrigerants for vapor compression cycle. For vapor compression refrigeration, so different types of refrigerants can be used. And the minimum properties required for the working fluid or the refrigerant is it should have high latent heat of vaporization. So whenever it has a high latent heat of vaporization, more heat can be taken away from the evaporator, that is to be refrigerated. Then high density of suction gas. So if the density of at the suction of the compressor, if it is high density, then the mass of the refrigerant required will also be less. Then it should be non-corrosive, non-toxic and non-flammable. So these are the safe working properties required for the refrigerant, and it should have high critical temperature. Okay, and it should have compatibility with materials of construction. So if the material used for condenser and evaporator, so that may be aluminum or brass, so it should have compatibility with reference to the refrigerant. Otherwise, some corrosion will be taking place, pitting will be taking place. So all these to be taken care before selecting the refrigerant. And it should have convenient working pressures. So at the condenser and also at the evaporator. So condenser pressure should not be very high and evaporator pressure should not be very lower than the atmospheric pressure. It should be positive pressures. Okay. Then high dielectric strength should have with reference to the compressor. and the cost of the refrigerant should be less also, and easy to detect also. The main disadvantage of Freon is that detection of leakage of refrigerant is very difficult task. Okay, so that's why here many hazards will take place, and also it should be environmentally friendly also. There should not be any ozone depletion due to high temperatures with the release of this refrigerant and also. So we'll see the properties in detail in the third unit. Next. Back and so back. Then effect of foreign material over the refrigeration cycle. So whatever the foreign material that is available is always air. Okay. So if air is mixed with the refrigerant, then what are the disadvantages are that? So the heat transfer may not be proper in the condenser, and it is not proper refrigeration effect will be produced in the evaporator. So all these disadvantages are there. Okay, let us see one by one. So air coming in does not take part in the refrigeration process, and it is to be compressed in the compressor. Okay, so which will increase the work input required in the compressor, and it prevents the refrigerant coming in contact with condenser and evaporator. So with that, what will happen here is the size of the evaporator required will be more, or otherwise. So here the amount of the refrigeration produced will also be less. And also in the condenser, so condensation is also not proper. Okay. So with that, here the work required will always be more, and vacuum required will also be reduced. So which is to be maintained in the evaporator and also in the condenser. So when high pressure liquid containing air is passed through the expansion valve. Okay. So when high pressure liquid that is coming from the condenser is passed through the expansion valve, so the refrigerant will be expanded to a lower temperature and pressure, but air may not expand. So with this, what will happen here is, so whatever the refrigerant that is coming from the expansion valve will be always at a higher temperature. Okay, because air is not expanded, which will be at a higher temperature, so that will add some heat. Okay, so due to that, here the refrigeration effect produced in the evaporator will also be less. So already we have seen a simple saturation cycle. So what is simple saturation cycle? So that is the cycle of the vapor compression system. At the inlet of the compressor, the refrigerant is dry and saturated. At the end of the condensation, so the refrigerant is saturated liquid state. Okay. So here with the flash chamber. So flash chamber is a device here, so which will be such that it will be kept after the expansion valve here. Okay, so which will send only the liquid refrigerant into the evaporator, and it will separate the vapor present. So when vapor is not passing through the refrigerator and only the liquid refrigerant is passing, more refrigeration effect can be produced. Okay, that vapor will be directed directly into the compressor. So with this, the evaporator size can be reduced. That is the main advantage of this. Next. So this is a simple saturation cycle with the flash chamber. So you can see the diagram here. So compressor, condenser, expansion valve. Then afterwards, a flash chamber is there between the expansion valve and the evaporator. So that flash chamber will separate the vapor, and vapor directly goes into the suction of the compressor, and only the liquid refrigerant is passed through the evaporator. Okay. So only when liquid refrigerant is passing through the evaporator, so more amount of heat will be removed from the chamber, that is the evaporator, and after taking the heat, so it will go as dry and saturated state, directly it goes into the compressor. So the same thing shown in the pH diagram. So one is nothing but the suction of the compressor. So 4 is the point at which here the expansion is taking place. So here it is in the wet state. It consists of some amount of water, some amount of liquid. So here the liquid present will be always more. So that liquid refrigerant will go into the evaporator, and whereas the vapor is separated, it directly goes into the compressor. Okay. The main advantage of this is it will reduce the size of the evaporator required by installing a flash chamber between an evaporator and a expansion valve. Next. Then single stage vapor compression cycle means it consists of only the required 4 components. So that is compressor, condenser, then evaporator, in between an expansion valve. Okay. So with this the coefficient of performance very less. Okay. When it is less is whenever the required temperature in the evaporator is very less. So for example, it requires some 40 degrees temperature inside the evaporator. Okay. For liquefaction of the gases, okay, it requires mainly for nitrogen, minus 150 degrees centigrade temperature is required. Okay. Whenever the required temperature in the evaporator is very less, in that case COP will be always less. Okay. So whenever the temperature required is less, then also the suction pressure will also be very lower than atmospheric pressure. Okay. So with that COP will be less. And also whenever the condensation temperature required is more, for example some 70 degrees centigrade or 100 degrees centigrade is required in the condenser. In that case also the coefficient of performance of the vapor compression cycle is very less. Okay. To increase the coefficient of performance, we have to go for multi-stage vapor compression refrigeration. So multi-stage, that name itself indicates, so there are number of stages in which the refrigerant is passing. It may require 2 compressors or 3 compressors, or maybe it requires number of flash chambers, or even it also requires reducing valves also. Okay. So the vapor refrigerant needs to be delivered to a condenser at very high pressure. Okay. Whenever we talk about the temperature, it implies pressure also. Okay. When suction pressure required is very less, means the suction temperature will also be less. Okay. Similarly, whenever the discharge temperature, that is the condenser temperature is required is very high, then the discharge pressure will also be high. So in that case, low temperature refrigeration systems. So this is the main requirement for low temperature refrigeration systems. So in such cases, either we should employ one compressor with high pressure ratio. Okay. So whenever suction pressure is less and the discharge pressure is high, it implies that the pressure ratio required is very high. Okay. Whenever the pressure ratio required is very high, then single stage compressor may not have that compression ratio. In that case, so it is to be compressed in number of compressors. So that is multi-stage compression. Then the compression carried out in 2 stages or 3 stages or 3 compressors is called as multi-stage compression. So the compression work can be reduced by using number of compressors. If the whole compression is taking place in a single compressor, then the size of the compressor required will be very large also. Okay. So if multiple compression is used, multi-stage compression is used, so number of compressors are used. So for each compressor, the pressure ratio will also be less. So which will reduce the size of the compressors, and also which will reduce the total work required for the number of compressors. Next. So let us see the advantages of multi-stage vapor compression refrigeration systems. So the main advantage of multi-stage compression systems are that the work done per kg of refrigerant is reduced. So what we discussed is, so if number of compressors are used, the total work required for all compressors will be always lower than that of the work required for a single compressor. and it improves the volumetric efficiency of a compressor for a given pressure ratio. So the efficiencies which are important for compressors, volumetric efficiency and isentropic efficiency, all these. So with this we can improve the volumetric efficiency, and also because the pressure ratio required is small for number of compressors, so leakage problem can also be avoided. Okay. So it reduces the leakage loss considerably. So it gives more uniform torque, and hence the size of the flywheel needed is also less. And also the other requirement for reciprocating compressors. So it always requires lubrication. So it provides effective lubrication also whenever the pressure ratio required is less. And also it reduces the cost of the compressors. Next. So there are different types of multi-stage vapor compression refrigeration. So let us see. So there are two-stage compression with a liquid intercooler. Then the second type is two-stage compression with water intercooler and also subcooler. And already we have seen that subcooling will increase the refrigeration effect. Okay. So here in this there is intercooler and also subcooler. So subcooler will increase the refrigeration effect, and similarly the water cooler, by using water cooler between two compressors, will reduce the work input to the compressors. And similarly two-stage compression with water intercooler and liquid subcooler and even also flash intercooler. And similarly two-stage compression with liquid intercooler and three-stage compression with flash chambers, three-stage compression with water intercoolers. So like that number of types are there for multi-stage compression. So the main aim of this multi-stage compression is to reduce the work input and also to increase the refrigeration effect and also avoid leakages and all those. Next. So this is the two-stage compression with the liquid intercooler. Okay. So there are two compressors and in between there is an intercooler. Okay. With this, what is done here is, so in the first compressor, the compression takes place in the first compressor. After that, it goes into an intercooler where heat rejection takes place at constant pressure. Then again, the compression takes place in the second compressor, and the remaining condenser, expansion valve, all these are same. So there is only the difference here is there are two compressors, and in between these two there is an intercooler. Okay. So with this, so 1 to 2 is compression, 2 to 3 is heat rejection at constant pressure in the intercooler, and again 3, 4 is compression in the second compressor, and 4, 5 is heat rejection in the condenser, and then 5, 6 is expansion, so which is isenthalpic, and 6, 1 is the refrigeration effect produced. So with this we can able to reduce the work required for the compression. Okay. Because here the work required in a single compressor requires more amount of work input. By using two compressors and by reducing the pressure ratio required for each compressor, we can able to reduce the total work input. The refrigeration effect is same, so it is not reduced or increased, but the work input to the compression process is reduced. By that way we can able to increase the coefficient of performance. And here always COP increases for vapor compression cycle whenever the compression process is very nearer to the saturated vapor line, and also the expansion process is nearer to the liquid line, then we can get more COP. So this is the method used by which here the compression is very nearer to the saturated vapor line. So like that here the work input is reduced and the COP is increased. Next. So this is a three-stage compression with flash chambers. So already we have seen flash chamber is a device which will separate the vapor from the liquid. Only the liquid refrigerant goes into the evaporator to be goes into the compressor. Okay, so like that we can able to reduce the evaporator size by installing a flash chamber after the expansion valve. So here in this, the 3-stage compression with flash chambers. So in the flow diagram you can see one HP compressor, LP compressor and also LP compressor, and then condenser, and there are 2 flash chambers and 3 expansion valves. Okay, so in the compression process here 1 to 2 is nothing but the compression in the first compressor, and 3 4 is the compression in the second compressor, and 5 6 is compression in the other compressor. Okay, so whereas in the expansion process here, because there are 3 expansion valves. Okay, so 7 to 8 is expansion in the one expansion valve. Again 9 to 10 is expansion in the other expansion valve, and 11 to 12 is expansion in the other expansion valve. So with this we can say that the expansion process is very nearer to the liquid line. Okay, whereas in the previous, if you see previous diagram, so there is only single expansion valve. Okay, so from 5 to 6 the whole expansion is taking place only in single expansion valve. So that's why this expansion line is not nearer to the liquid line. Okay, whereas in the second case we can by using 3 expansion valves, so we can able to get the expansion process very nearer to the liquid line. Okay, so with this we can get more refrigeration effect also. So remaining process are same. So 12 to 1 is nothing but the actual refrigeration effect produced, and similarly 1 to 2 is compression. At 2 here it goes directly into the other compressor, and similarly 3 4 is compression, 5 6 is compression. Then all this discharge vapor goes into the condenser for condensation. So finally the vapor is condensed to 7. Then so 7 to 8 is expansion in E3. Okay. Then after that when it goes into the flash chamber here, only the liquid refrigerant, okay, so goes into the evaporator. So whereas here the vapor is separated, directly goes into the HP compressor. So we can get more COP because here the liquid line is also nearer to the expansion is the process is nearer to the liquid line. Next. So this is a multi-load system. So whatever we have discussed in the previous two, there is okay. So the required evaporator, that temperature required in that evaporator is constant. So whereas in the multi-load system means it consists of number of evaporators. By that way we can able to change the temperature required in different evaporators. Okay. So here in this figure you can see E1, E2, E3. These are the 3 evaporators required. But here this is a multi-load system with single evaporator. Okay. So these 3 evaporators are, let us assume these 3 evaporators are connected to 3 different chambers. Okay. Where the required refrigeration is also same. If you have some 3, so in that case here, so some amount into this room, that room, that room. But all the temperatures are same in all the 3 evaporators. So this is the case of 3 evaporators, 3 different evaporators maintained the same temperature. So only one expansion valve, one condenser and compressor. So whatever the pH diagram that is shown is for a evaporator. Okay. So which is maintained at the same temperature. So like that. So there are 3 evaporators which can maintain the required temperature in the evaporator. So with this we can find out what is the mass of the refrigerant required in the first evaporator, second evaporator and also third evaporator. If T1 is required evaporation evaporator and T3 is the required tonnage required in the third evaporator. In that case, what is the mass of the refrigerant required for the first evaporator? So if you know T1, 3.5 into T1 by, so the work input required, so that is H1. So similarly, mass of the refrigerant going into the second evaporator. So that is 3.5 T2 by, again H2 minus H1. So like that, what is the total power required? Is but so M1 plus M2 plus M3 into H2 minus H1. So many kilowatt. Next. So this is the multi evaporators at different temperatures and with different expansion valves. So there is a single compressor, condenser, but 3 evaporators are required at different temperatures. Okay. For this 3 expansion valves are connected, and above that we can see those are back pressure valves or pressure reducing valves are also called as pressure reducing valves. So here with this what we can say is at the suction of the compressor the refrigerant is in the state of X. Okay. So X to 5 is the actual compression in the compressor and 5 to 6. Okay. So 5 to 6 condenser. Okay. Then at 6 it goes into different evaporators, different temperatures through number of okay. So at the end of condensation the refrigerant coming at 6 goes into the first expansion valve and then it comes at 7. Okay. So the refrigerant is coming from the first expansion valve at 7. Okay. Then the refrigerating effect required in the evaporator is only H. So that is the refrigeration effect produced, that is shown in the pH diagram. So similarly at 6 the refrigerant goes into the second expansion valve. Then from 6 to 8. So 6 to 8 is nothing but the expansion in the second required temperature in the evaporator here. So at that 8.3 is nothing but the actual refrigeration effect produced in the second evaporator. So similarly at 6 again it goes into the first evaporator which is at the last one, and the expansion is taking place from 6 to 1. Okay. 6 to 1, and at 1 it goes into the first evaporator where the refrigeration effect produced is H2 minus H1. Okay. So after getting the required refrigeration effect here, so finally from the pressure reducing valve, so at 4 again the refrigerant goes into pressure reducing valve, and again at 2 it goes into the expansion valve, pressure reducing valve, and again at 3 again it is going into the pressure reducing valve. So which will reduce suction. Again all these are mixing and go. This is the case for multi evaporators. So evaporators are maintained at different temperatures. So for this 3 expansion and also here 3 reducing. So the function of the pressure reducing valve is to reduce again the pressure to the required suction pressure. So all these are mixing and coming at X. Okay. So finally at the suction of the compressor the refrigerant is at the state of X, and X5 is the actual compression in the compressor. So with this also we can find out what is the mass of the refrigerant required for the first evaporator, which requires T1 tonnage of refrigeration, which is equal to 3.5 into T1 by work input. Okay. That is H2 minus H1. So 3.5 T1 by the refrigerating effect produced. So that is H2 minus H1. So that is the refrigeration effect produced in the first evaporator. So similarly for the second evaporator, the mass of the refrigerant required is 3.5 into T2 by, so the actual refrigeration effect produced in the second evaporator. So that is H3 minus H8. Okay. So similarly the refrigeration effect produced in the third evaporator is H4 minus H7. So with that, for all the three evaporators. And finally you can find out COP also. Coefficient of performance of this one is, so M1 into H2 minus H1. So plus M2. M2 is nothing but the mass of the refrigerant going into the second evaporator into the refrigeration effect produced. So that is H3 minus H8. Okay. Plus again M3 into, so the second, in the third one, what is the refrigeration effect produced is H4 minus H7. So with that we can able to find out COP of the multiple evaporator system. Next. So this is a diagram showing the vapor compression refrigeration cycle in PV diagram, TS diagram and also HS diagram. So whatever chart is available for that refrigerant, so directly you can use this to find out the refrigeration effect or to find out the superheating temperature T2, or otherwise what is the heat rejected in the condenser, work required for the compressor and all this. Okay. And the isenthalpic process 3-4. So shown in the HS diagram here. So this type of diagram is more used. Take one problem on this. Of the compressor. At the suction of the compressor, the refrigerant may be saturated condition. At the discharge, it may be superheated condition. Or otherwise, at the suction of the compressor, it may be in wet state. Or at the discharge of the compression, it may be in the superheated condition. So, for all this, you have to first find out all the 4 enthalpies. Okay. So, 3 enthalpies are sufficient and the other 4 is nothing but H4 is equal to H3. Next. Note down this problem. 20 tons of ice is produced from water. 20 ice is produced from water at 20 degrees centigrade to ice minus 6 degrees centigrade. The compressor is from minus 50 degrees centigrade to 25 degrees centigrade. So that is the evaporator. At minus 15 degrees centigrade, so the liquid enthalpy is minus 54.55 kilojoules per kg and the entropy is minus 2.1338 kilojoules per kg Kelvin. And for the vapor, the enthalpy is 1304.99 kilojoules per kg, and the entropy is 5.0585. Okay. So at the suction of the compressor, the vapor is in the wet state. At the discharge of the compressor, the vapor is dry and saturated. Okay. So first thing is you have to find out the known by equating the this. Okay. So entropy at 2 is directly known. Entropy at 2 is nothing but at 25 degrees centigrade the entropy of the vapor. So that is 4.4852. Okay. So which should be equated to find out the dryness fraction at 1. So the dryness fraction at 1 is at minus 15 degrees centigrade SF plus X into SFG. Okay. So S2 is directly known from the properties equal to 4.4852. So that should be equated to find out the dryness fraction at the suction of the compressor. So that is SF plus X into SFG. So when you fraction at X, so the dryness fraction at 1 X is equal to 0. Find out the enthalpy at 1. So that is again HF plus X. So that is at minus 15 degrees centigrade. So see the values of H of liquid. So that is 54.55 minus 54.55 plus the dryness fraction. What we calculated is 0.92 into, so H vapor minus H liquid. So that will give you at 1 or at A, that is the suction of the compressor, the enthalpy is 1196.22 kilojoules per kg. And HB, so HB is directly known. So because that is dry and saturated state at 25 degrees centigrade. So the vapor enthalpy is HB. So that value is directly given from the properties, that is 1319.2. Then you find nothing but at the end of the station there is a liquid state. Okay. So the liquid enthalpy at 25 degrees centigrade from the properties. So that value is equal to 100.04 kilojoules per. So H4 and H3 is equal to 100.04. So all the effect is HA minus HD. So you know HA, you know HD. So find out the difference to get the refrigeration effect in kilojoules per kg. Then again you find out the work input. So work input is HB minus HA. So HB value is 1319.2 and HA value is 1196.22. So the work input is 122.98. So with this you can find out the coefficient of performance, that is the ratio of the refrigeration effect to the work input. So that value is 8.913. And here it is given that the actual COP is, so 80% of the COP. Okay. So because the relative COP is given as 0.8, so find out the actual COP, which is 7.13. So our main aim is to find out the work input. Okay. So actual COP is 7.13. So here what is the total refrigeration capacity you have to find out. Okay. So that is at 20 degrees centigrade to form ice at minus 6 degrees centigrade. So that is inlet temperature 20 degrees centigrade and water is to be formed to ice at 0 degrees centigrade. Plus again it is to be formed into ice. So you have to add latent heat of ice. And ice is not formed at 0 degrees centigrade. It is to be formed at minus 6 degrees centigrade. So that's why again you have to take Cp of ice into 0 minus 6 degrees. So with that it is extracted kg of ice. So that is 430. Then what is required? So mass of ice required here is that is 20 is required. Okay, the total tonnage required is that is per day. It is given per second. Find out actual heat extracted per second. So mass of the ice to be formed into heat extracted. So that is equal to 99.84 kilojoules per second. So already we have seen actual COP is 7.13 and we have already calculated actual heat to be extracted per second. Okay, because COP is heat to be extracted by the actual work input. So with this we can find out what is the actual work required in kilowatt. So that is 14 kilowatt. So here the problem is that at the suction of the compressor, the refrigerant is in the wet state, and at the discharge of the compressor, the refrigerant is in the saturated vapor condition. Next. So now take the another problem. A vapor compression refrigerator working with Freon 12 has its temperature range minus 10 degrees centigrade and 30 degrees centigrade. So the evaporator is to be maintained at minus 10 and the condenser at 30 degrees centigrade. The vapor enters the compressor dry and undercooled by 5 degrees centigrade in the condenser. So at the suction of the compressor, here the refrigerant is dry and saturated vapor. Then at the end of the condensation, so it is liquid and it is again subcooled by 5 degrees centigrade. For a capacity of 50 tons of refrigeration, determine the coefficient of performance, mass of the refrigerant and the power required. And for this Cp of vapor is given and Cp of liquid refrigerant is given. So Cp of vapor is 0.56 kilojoules per kg Kelvin and Cp of liquid refrigerant is 1.003 kilojoules per kg Kelvin. And the properties of Freon 12 at the required temperatures are given. So at a condensation temperature of 30 degrees centigrade, so enthalpy of the liquid given, enthalpy of the vapor given, and also the latent heat is also given. So similarly, for the entropy entropy of the liquid refrigerant given and the entropy of the vapor refrigerant is also given. So note down the properties. So with these properties, find out the enthalpy H1, H2, H3 and again H4 to find the COP and mass of the refrigerant and the power required. Next. So A is at the suction of the compressor, it is given that it is dry and saturated. So obviously at the discharge of the compressor, the refrigerant will be always in the superheated condition. And so it is given that, so it is at the end of the condensation, it is subcooled by 5 degrees centigrade. Okay. So C is here given as liquid condition here, and subcooling is also taking place by 5 degrees centigrade. So first thing is note down the enthalpy at A. So that is at the required temperature of back. So that is at evaporated temperature of 10 degrees centigrade. Note down the value of Hg. So because that is dry and saturated. Okay. So H1 HA is 183.19 kilojoules per kg. Then find out the value of H2. So for finding H2, so first thing is you have to find out T2, that is the superheating temperature. So for that you equate the entropies. So entropy at 1, so that is at minus 10 degrees centigrade, Sg value is 0.701. So that should be equated to Sg plus Cp of vapor into ln Tb by Tb dash. Okay. So Tb is the superheating temperature. So that is to be known. So for finding the superheating temperature, you should equate the entropies. So entropy at A is known. Entropy at B is nothing but here. So 0.6853 plus Cp of vapor into ln T superheating temperature by T saturation temperature. So saturation temperature is already given as 30 degrees centigrade. So convert that to Kelvin. So with that you find out what is the superheating temperature at the discharge of the compressor. So that is 312.15 Kelvin. So after knowing TB, then find out HB. So HB is nothing but, so at 30 degrees centigrade, Hg plus Cp of vapor into T superheating temperature minus T saturation temperature. So that is Hb dash, Hb minus Hb dash. Okay. So that value gives actual Hb. So that Hb, you find out that. So that is 204.74 kilojoules per kg. Then after finding Hb, next you have to find out Hc. Okay. So Hc is nothing but it is superheat. It is in the subcooled state. Okay. So that curve is not completely given. So from B dash to C dash should be there, and after that it should pass through the liquid line. Okay. So C dash and C. So this is B, this is B dash. So this is important for us, A, then C. This should be C, and somewhere it should be C dash. Okay. So this curve is missing in the figure here. So directly you can know Hc dash. So Hc dash is nothing but at 30 degrees centigrade. What is the value of the liquid refrigerant? Okay, but here you have to find out this Hc, okay, because the refrigerant is subcooled by degrees centigrade. So that enthalpy you should find out Hc. So how to find out Hc? So that is Hc dash minus Cp of liquid into Tc dash minus Tc. Okay, that difference is 5 degrees centigrade. So Hc dash is nothing but already you know at 30 degrees centigrade the value of the liquid enthalpy, and here the heat is to be removed. That subcooled heat should be removed to get Hc. So that value is nothing but here. So 64.59 minus Cp of liquid 1.003 into, so how much temperature it is subcooled 5 degrees centigrade. So 30 minus 25. So that directly gives Hc value. So Hc is 59.575. So Hd is again equal to Hc. So that is again equal to 59.575 kilojoules per kg. So after getting all four enthalpies, find out the refrigeration effect and work input. So refrigeration effect produced is HA minus HD. So HA minus HD, and the work input required is HB minus again HA. Okay. So the refrigeration effect produced is 123.61 kilojoules per kg, and the work input is 21.55 kilojoules per kg. After finding these two, find out the coefficient of performance. So coefficient of performance is the refrigeration effect by the work input. So it is 5.73. And to find out the mass of the refrigerant here, first thing is you have to find out what is the refrigeration capacity. So whatever RE you have found is the specific refrigeration effect required. Okay, that is per kg of the refrigerant. So to find out the mass of the refrigerant, first find out the refrigeration capacity. It is given that it is for 50 tons. Okay. So directly in kilojoules per kg, if you multiply that with 3.552, you can directly get that the refrigeration capacity 52.5 kilojoules per kg. And already you have found the refrigeration effect per kg. So first find out what is the mass of the refrigerant, that is freon required. That is the ratio of the refrigeration capacity to the refrigeration effect produced per kg of the refrigerant. So with that, the mass of the freon or the refrigerant required is 0.425 kilojoules per second. Then to find out the total power required, so mass of the refrigerant into the work input per kg of the refrigerant. So that is 0.424 into the work input is 21.55 kilojoules per kg. So the power requirement for 15 tons of refrigeration is 9.152 kilowatt. So in this problem, only the difference between the previous one and this one is at the suction of the compressor, the refrigerant is dry and saturated vapor condition. Okay, and also the refrigerant is subcooled by 5 degrees centigrade. Then next. So note down another problem. So this is the design of the compressor. How much bore is required, stroke is required. A food storage locker requires a refrigeration system of 12 tons capacity at an evaporator temperature of minus 8 degrees centigrade and a condenser temperature of 30 degrees centigrade. The refrigerant is Freon 12 is subcooled to 25 degrees centigrade before entering the expansion valve. And the vapor is superheated to minus 2 degrees centigrade before entering the compressor. The compression of the refrigerant is reversible adiabatic. A double acting compressor with stroke equal to 1.5 times the bore is used, operating at 900 RPM. Determine the COP. Theoretical piston displacement per minute. Mass of refrigerant to be circulated per minute. Then the bore and stroke of the compressor. Then specific heat of refrigerant. Specific heat of the liquid refrigerant is 1.23 kilojoules per kg Kelvin. And specific heat of vapor refrigerant is 0.732 kilojoules per kg Kelvin. So in this problem, the deviation from the previous problem is that at the suction of the compressor, the refrigerant is in the superheated condition. So the actual evaporator temperature required is minus 8 degrees centigrade. But the refrigerant at the suction of the compressor is superheated to minus 2 degrees centigrade. Okay. So it is superheated by 6 degrees centigrade. So minus 8 to minus 2. Then again there is subcooling also. So the condenser temperature is 30 degrees centigrade, but it is subcooled to 25 degrees centigrade. So subcooling is by 5 degrees centigrade. Okay. So there is superheating and also subcooling. And in addition to that, you have to find out the bore and stroke of the compressor. Next. So that is the diagram. TS diagram shows both superheating and also subcooling. Okay. So the required temperature in the evaporator is minus 8 degrees centigrade. But at the suction of the compressor, so it is at minus 2 degrees centigrade. And similarly B. So that is the condenser temperature required is 30 degrees centigrade. But it is subcooled to 25 degrees centigrade. Okay. Combination of both superheating and also subcooling. So like the previous one, here also you have to find out all the enthalpies to find out the work input or the refrigeration effect. So AB is the isentropic compression process. So entropy at A is equal to entropy at B. So entropy at A, here at A, you know what is the superheating temperature, minus 2 degrees centigrade, and the evaporator temperature is minus 8 degrees centigrade. But the discharge temperature B, TB should be known. Okay. For finding the temperature TB, so what is done here is equating the entropies at A and entropy at B. So entropy at A is nothing but Sg. So at minus degrees centigrade, the value of the vapor entropy plus specific heat of the vapor refrigerant into log E to the base of vapor refrigerant into log B by log B dash. So similarly at the suction also same. So at minus 8 degrees centigrade, you know the value of Sg. So Sg plus specific heat of the vapor refrigerant into log E to the base of Ta by Ta dash. A dash is not given in that figure. So this is A and this is A dash. So this is minus 8 degrees centigrade and this is minus 2 degrees centigrade and this is 30 degrees centigrade and this is 25 degrees centigrade. So to find out HA, so you have to equate SA with SB. Okay. So SA is nothing but specific heat of vapor into ln TA by TA dash plus S of G at minus 8 degrees centigrade. So that should be equated to SB. SB is nothing but SG at 30 degrees centigrade plus Cp of the vapor refrigerant into ln TB, that is the superheating temperature, by the saturation temperature. So with all this, our aim is to find out the superheating temperature. Okay, that is the discharge temperature of the compressor. So at the discharge, the refrigerant is having the temperature of 317.22 Kelvin. So after finding TB, next step is to find out enthalpy at B. Okay, so enthalpy at B is nothing but N. So enthalpy at the saturation temperature of 30 degrees centigrade, the vapor refrigerant plus again Cp of vapor into TB minus TB dash. So with that you can find out HB. HB value here is 210.02 kilojoules per kg. After finding this, you have to find out HC. So HC value is nothing but here HC dash minus the heat rejected due to subcooling. So HC dash directly you can get from the properties. So that is at 30 degrees centigrade, the liquid enthalpy. Okay, so that is HC dash. So minus Cp of the liquid refrigerant into 5 because it is subcooled by 5 degrees centigrade. Then find out the value of HC dash. Okay, so the same thing here, it is given as HC. That HC value here is 58.4 kilojoules per kg. So after finding all the 4 enthalpies, find out the work input, find out the refrigeration effect produced. So with that, find out coefficient of performance. So coefficient of performance is 6.07. Okay. So after finding the coefficient of performance, go to the next. Then find out the mass of the refrigerant. So here it is given that it is for 12 tons of refrigeration. Okay. So mass of the refrigerant required is the total refrigeration capacity by the refrigerating effect produced per kg of the refrigerant. So 12 into 3.5 by 130.18. So it gives 0.322 kg per second, but it is asked in kg per minute. Okay. So we convert that to kg per minute. Then next step is to find out the bore and stroke. Okay. So for that you equate PV by T is constant. Okay. So that is at the suction of the compressor. So PVA by TA is equal to, so PV by TA dash. Okay, VA dash by TA dash. So VA is nothing but the actual suction volume, okay, for the compressor. So which is equal to, here pressure is constant. So VA is equal to TA into, so V gas at A dash by TA dash. Okay. So TA is given as minus 2 degrees centigrade. And TA dash, so TA dash is nothing but minus 8 degrees centigrade. And the volume of the vapor is given 0.441. So with you find out what is the volume of the refrigerant at the suction of the compressor. So you equate that to 5 by 4 d square ln. Okay. So because this is a double acting one, so it should be multiplied with 2. 2 into pi by 4 d square ln. Okay. So here volume is equal to 2 pi by 4 d square ln. So where L is given as 1.5 times that of the bore. So if you substitute L equal to 1.5 d in that relation, then you can find out the value of L first, then D. Okay. So bore is 7.38 centimeters and the stroke is 11.08 centimeters. Okay. So in this only the additional problem given here is to find out the bore and stroke. So remaining problem is superheating and also subcooling. So you take this problem for homework. A vapor compression refrigeration system of 5 kilowatt cooling capacity operates between minus 10 degrees centigrade and 30 degrees centigrade. The enthalpy of refrigerant vapor after compression is 370 kilojoules per kg. Find the COP, refrigerating effect, mass of the refrigerant and the compressor power and the properties of the refrigerant are given. So that is at the evaporator temperature of 10 degrees minus 10 degrees centigrade and the condensation temperature of 30 degrees centigrade. So even pressures are also given. So the difference between the previous problems and in this problem. So at the suction of the compressor, what is the state of the refrigerant? Is it given dry or wet? But at the discharge of the compressor, the enthalpy of the refrigerant is directly given. So no need to find out the temperature, superheating temperature. So it is directly given as 370 kilojoules per kg. Okay. So you first assume that at the suction of the compressor, it is dry and saturated. Okay. Next. If nothing is mentioned, you can assume that at the suction of the compressor, the refrigerant is dry and saturated. So HA value is nothing but the enthalpy of the refrigerant, that is at minus 10 degrees centigrade, the vapor enthalpy. And so HB is also given. Okay. So that value directly is given 370 kilojoules per kg. No need to find out the superheating temperature and then finding the enthalpy. So directly HB is given. And HC value also directly you know. So at the condensation temperature, so the liquid enthalpy and HD is also known. Okay. So find out the remaining. Only the difference here from the previous one is that, so without finding the superheating temperature, so directly enthalpy is given. So it's simple problem. Okay, you can do this. Next. So note down this also for homework. A vapor compression refrigerator uses methyl chloride and works in the pressure range of 1.19 bar and 5.67 bar. So from the methyl chloride charts, you have to take the properties. Okay, I have given the properties directly, but actually you have to take the properties from the table. So at 1.19 bar, you see the what is the saturation temperature. Okay. So after finding the noting the saturation temperature, at that temperature, note down the properties of liquid enthalpy, vapor enthalpy, latent heat, and also entropy of the gas, entropy of the liquid. At the beginning of compression, the refrigerant is 0.96 dry. So at the suction of the compressor, it is the refrigerant is in wet condition having the dryness fraction of 0.96, and at the end of isentropic compression, its temperature is 55 degrees centigrade. The refrigerant liquid leaving the condenser is saturated. If the mass flow of refrigerant is 1.8 kg per minute, determine COP, the rise in temperature of cooling water. If the water flow rate is 16 kg per minute, so that is in the condenser cooling water is used. So the rise in temperature of cooling water, so that temperature you have to find out for the mass flow rate of 16 kg per minute. So the main difference between the previous problems and this problem is that the suction of the compressor, the dryness fraction is given. Okay, and even the discharge temperature is also given as 55 degrees centigrade. So no need to find out even the superheating temperature also. Okay, so simply you have to find out enthalpy at B. So 55 degrees centigrade and the actual condensation temperature is 30 degrees centigrade. Okay, 55 minus 30 into specific heat of vapor plus the saturated vapor enthalpy. Okay, if you add that, then you will get HB. So after finding this, you have to equate what is the heat removed in the condenser equal to heat gained by water in the condenser. Okay, so that MCP delta T should be equal to again MCP delta T of the refrigerant. Okay. Next. So rise in temperature, you have to get this as 10.7 degrees centigrade. So you try these two problems as homework. So one of you can conclude the today's lecture. So next class we will see some more problems on vapor compression, and we'll go to third unit. So that is refrigerants.
Like wet compression, dry compression, and differences between the wet and dry compression, and advantages and disadvantages. And we have dealt with number of problems too, how to calculate the temperature rises and coefficient of performances, etc. and etc.
So we have also discussed about multi-stage vapor compression system. Okay, and we have seen the advantages of multi-stage. Okay, when multi-stage is preferred, whenever the evaporator temperature required is very low. Okay, and condensation temperature is very high. Okay, in that case, because the work input by single compressor will be always more, so multi-stage is preferred. Okay, and also multiple